long and rather uncomfortable day perhaps in this rather hot room, what I'm going to do as this final talk is to try to show you maybe something a little bit different, but maybe related at a sort of more fundamental level, which is how we have, not only are there defects in condensed matter systems, there are also defects in optical systems. That is to say, light fields that are in free space or indeed propagating in materials. And what I will be talking about is topological optics, that is to say, thinking about how we apply topology to describe optical fields. And although the title was liquid crystals, I actually think that I'll be talking about crystals that aren't liquid to make some of my points a little bit more clearly. So, of course, one of the things that we all are interested in with liquid crystals, and one place that it touches light, is of course the idea that light is polarized. And if light is polarized, of course, that's what we use to be able to have liquid crystal displays, to be able to, such as this data projector, to be able to use their, take advantage of their interesting optical properties. And it's interesting to observe polarized as a word was invented by Malus about just over 200 years ago, coined it in March 1811. And this comes from, well, it's the Oxford English Dictionary, I'm afraid, here we are in Cambridge. But what I'm going to talk about, rather than actually the definition, which I'm sure everybody in this room knows, I want to just talk a little bit about the etymology, where the word comes from. So it was a comment on his paper in giving to the sides of the ray, so the light ray is going this way, the name of poles. Malus calls a modification which imparts light property relative to the poles, polarization. This new expression signifies simply modification that light has undergone in acquiring new properties relative not to the direction of the ray, but to its sides. So even Newton talked about the sides of a light ray. And the idea is that, of course, polarization is not a vector, it's a director. And the editor of the dictionary here makes that point. The choice of the word polarization unfortunately assumed a sense of pole quite different from its use in astronomy, geography and magnetism, with the consequence that polarization as applied to light and radiant heat has nothing in common with magnetic or electric polarization. That is to say, we talk about these things when we talk about polarized light, not these things which we would talk about if we were talking about dipoles. And it turns out that observation has a profound significance about optical properties of things all around us. So here's one of my favourite examples. It's a picture of the blue sky where there are no clouds, and the small line segments here are the direction of polarization. That is to say, my colleague who made the experiments, the observations, he just took a piece of polarizer like this and he turned it around. And the whole point of it being direct to light is you can't see any difference between when you hold the polarizer like this and when you turn it by 180 degrees. That's because, of course, the real electric field is a vector, but it's wobbling up and down so quickly that you can't tell whether it's pointing up or pointing down. And so these are the directions of the polarization of the light in the sky. So what we've got is this is the point straight up, the zenith, and as radius comes out along this disk, the angle comes down like this, and this is the horizon. You can see there are some street lamps and so forth. And these are observations by my colleague Ray Lee, who always likes to make the joke that he's an atmospheric optics observer, so his main interest is in Ray Lee scattering. So the sun has just set in this picture, and so here's all of the polarization. You can see that it's a nice and smooth director pattern, apart from just above the sun, and just a point above the point in the sky opposite the sun. And they look pretty much, well, to this audience should be obvious, look like plus half disclination defects, about 15 degrees above the sun and above the point in the sky opposite the sun. So they're around us. Had we evolved to see polarized light, we would have known about plus half disclinations. There'd be mythology about it. There'd be love songs about it. So it's trying to convince you that these defects are in optical patterns all around us. So what I will try to do in the time I've got, I'll start by talking about the main sorts of defects we consider in optics. That is to say, optical vortices, that I'm sure many of you heard of. They're defects in scalar light fields. And then I'll talk about the polarization case and how you get spatial order in light fields. Then I'll talk about the crystal bit. That is to say, with the tools that we've built up, I'll be able to give you an account once and for all about why crystals with 3 different axes are called biaxial, not triaxial. Which I know often causes a lot of frustration amongst people. And if I have time, I'll talk a little bit about how disclinations can be different shapes in optics from the shapes one's used to seeing in liquid crystals. And I have this as a nice book by John Nye, and there's also a review by myself and some colleagues that talks about these things, and I can give you the references again at the end if you're interested. So these optical vortices, for the purposes of my talk today, are to think of them as defects in scalar light. So of course, to be able to talk about light, we represent light by complex scalar fields, and I'll come to that in a little bit more detail later. But the idea that we've got a 3-dimensional order parameter, which is a complex scalar, it's a bit like in quantum mechanics, where you have this complex scalar representing the probability amplitude. And we think of that representing the light field. And if I've got a complex scalar, then it has a real part and it has an imaginary part. And as I move around the real part, I'll find 0 surfaces, and I'll find for the real part, and I'll find 0 surfaces for the imaginary part. And of course, where those 2 sets of surfaces cross, the complex number is 0. So in general, I'd expect these zeros to be lines, filaments in 3 dimensions. And in 2 dimensions, they're points. And here's an example of a sample function where I'm plotting here the phase, the argument from 0 to 2 pi, and where all the phase lines come together. That is to say the complex number is 0. And they're called vortices because you can see that the phase either circulates, what am I doing? I'm going from dark blue to light blue, so that's going down. In the right-hand side, so this has got a negative sign, and this one has got a positive sign. But because they're zeros, and in some sense they're quite trivial in the sense that there's no physics that you expect to see after the vortices. They're just a generalized form of interference fringe. They're just places where the light is 0. And they arise naturally when I superpose different beams. But fundamentally, they carry no energy. So unlike in liquid crystals, where the defects tend to have 2 properties, that is to say, they're places where all of the energy is concentrated, and they're topological in nature, which means they organize the structure of the field. Here, we only have the second one. So there's no energy associated with these optical vortices, at least in the linear situations that I'll be talking about today. If we go to non-linear, the situation is a bit different, but I won't talk about that. So, just to maybe go into a little bit more detail, why is light a complex scalar? Why do we represent it as a complex scalar? Well, if we're thinking about a light beam, and let's think it's polarized, linearly polarized in the x direction, then the real electric field, depending upon position and time, is the real part of our complex scalar times e to the minus I omega t. So effectively, if we're talking about optical fields, the frequencies are so rapid that it doesn't actually make sense to talk about where it is at t equals 0 or at t is a small time interval afterwards, because the frequencies are so huge. So it's natural then to, well, at least if we're talking about laser light, so we can pull out this single frequency factor, to say, rather than talking about this explicit E field, we're talking about this complex field that doesn't have any time. And one of the reasons why electrical engineers like using this approach is because you can replace all that nasty trig with just multiplying by complex phase factors. So here's a sort of picture that as time evolves, so my colours change through 2 pi, that's the sort of thing that a small snapshot might look like over over a 2 pi interval. But what we see is the time averaged intensity. And within those time averaged intensity, there's some dark bits, and within those dark bits, there are some complete zeros, say here, and that would correspond to a point here that's always 0. There we go, twitches on. And so when we talk about vortices, somehow this is all circulating around this point of time. So that's why we use complex scalar functions to represent the electric field. And these ideas of phase singularities, these topological defects, are actually very general when the quantity that I'm trying to describe is naturally expressed in polar coordinates. So I've got some sort of intensity, it's like radius, and phase, which is like azimuth. And of course, even to represent the phase, I've been using this colour wheel. The colour wheel's a bit strange, because if I want to think of R, G, and B, that sounds like it's a nice Cartesian colour space of increasing the amount of red, increasing the amount of blue, and increasing the amount of green. So where does the phase come from? Where does this phase singularity come from? I'm not going to try any clickers, but if anybody's still awake, what's this got to do with 3-dimensional red, green, and blue colour space? Because this is pretty bad. There's a singularity there. Okay, let's put it along here. So the idea is, of course, if I have an equal amount of red, green, and blue, I don't have any colour. The equal amount of red, green, and blue is grey. So really, if I look at red, green, blue colour space as a 3-dimensional cube, so this is white, which is the 1, 1, 1 direction. In fact, every colour on the 1, 1, 1 direction doesn't have a colour. So if I use hue, that's actually the azimuthal angle around the 1, 1, 1 direction of colour space. And in fact, cylindrical coordinates in that colour space is what we call hue, saturation, and brightness. So in particular, what we have instead of intensity, the radial variable, is the saturation of the colour. Another question is, another point is we have a singularity of the angle your watch points if you go to the North Pole. Lots of people starting from different time zones, all walking to the North Pole, will have not have left their time zone, but will have a different angle pointing on their watch from the hour hand. So again, a question, what's the radial variable associated with this singularity, the thing that goes to 0? So the idea, of course, is that all we mean by time is it's a synchronization of the local maximum of the height of the sun. And so at the poles, the height of the sun never changes. And so it's a singularity. I can't synchronize my watch with respect to that. Okay, so that gives you an idea of the sort of the sort of topology, or what the physics, some physics or mathematics behind this topology is. And these things aren't exclusively studied in optics, and interestingly, the place they first showed up was in the study of the tides in the oceans, going back to, again, Cambridge in the early 1800s. So, well, even before that, Newton and Laplace knew that the tides of the ocean, they go up and down, satisfy a wave equation. Satisfy a wave equation, the bits that are high sort of rotate, they sort of advance, the high tides advance in the oceans. So the question was, could it be mathematically modelled? And of course the hard problem with modelling the tides is the boundary conditions, the depth of the ocean and the shape of the coast is very complicated. And Thomas Young suggested, well, why don't people actually just map it out, do the experiment, do the observation and see what it does? And these experiments were coordinated by William Whewell, who has a court named after him at Trinity College. And this is Whewell's picture of, this is the east coast of Britain, and here's Norway, and here's the Netherlands and Denmark. And what we've got here are the lines of high tide made by observations, coast guards, who measured that this is the line of high tide at 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, and so on. And what he saw was the only way of explaining this sort of rotating high tide in the English Channel is if there's a singularity in the middle of the ocean there. And he said this: the cotidal lines, the lines of constant phase, may be supposed to revolve around a point where there is no tide. For at a point where all the lines meet, it's high water at all hours. That is, the tide vanishes. So the idea then that there are these, that if I have something that's got a cyclical variable that's can't be defined, then assuming the function is smooth, so certainly the case for anything satisfying a wave equation, then the variable that describes it, the height, has to be 0. So just thinking, how do I see these things? I could just look at superpositions of plane waves. So here I've got now my psi square root of intensity e to the I chi. Chi is the phase. And so if I have a single plane wave, that's e to the I ky just travelling up the page. Let's say blue goes to red, it's travelling up the page, the spatial frequency. If I were to superpose two plane waves, it's like an interferometer. I get jumps of pi where the intensity goes to 0. That's like what you see in the number slits. But if I have 3 or more plane waves, this regular pattern is broken up, and I've got these singularities all over the place. The zeros, the nodes, are the same as the vortices in phase. And if I move to 3 dimensions, because often the situation is more interesting in 3 dimensions, I can get different topologies of these optical defects. So here's, again, a simple picture of the superposition of plane waves. I've got 3 plane waves that are fixed, they're going in certain arbitrary directions with the same weighting, the same amplitude, and I've got a 4th plane wave, and I'm just going to turn up the amplitude of the 4th plane wave, and we're going to see what happens to this forest of straight vortex lines, optical vortex lines. So if A4 equals 0, it's like 3-wave interference, and I've just got these straight lines. When A4 equals 1, the lines approach and reconnect. So just like you see with defect lines in liquid crystals, these things are more general. It's just topological, and the topology of these lines will change at these reconnections. And then when A4 equals 3, so that is to say that the 4th plane wave has an intensity larger than the sum of the other 3, and amplitude larger than the sum of the other 3, then there can't be any more zeros. So as we turn it up, you see they bend, there's a reconnection, they all become small loops that shrink down and vanish. So one of the things that can be done easily with these topological models is they're purely objects of linear superpositions. So there's no complicated modelling involved. You can just take Mathematica or MATLAB, whatever you like, and just twiddle the knobs and see the sort of things you get. And one of the reasons that this is interesting is because the topological phenomena are often very similar to situations which have far more complicated physics. One of the most important examples of these vortices appearing in the lab are, so using the laser beam equation, the paraxial wave equation, are so-called Laguerre Gaussian modes. And this is the rather fearsome looking formula for a Gaussian laser beam with a vortex up the axis. It's in cylindrical coordinates, and as you can see, as phi goes from 0 to 2 pi, the phase is going to change by 2 pi times L. And they're called Laguerre Gaussians because in order to satisfy this equation, the radial coordinate has to appear in this Laguerre polynomial. And they have two integer numbers, L and P. L is the total phase winding around the axis here. So LG10 is just a Gaussian with a 0 up the axis. And as we watch it propagate, you can see the phase swirls around, but it's just a straight line up the axis. An LG21 beam, if these are sometimes called donut beams, so I guess these are greedy donut beams, more than one ring. So 2,1, there's a 4 pi phase change around the axis, and the 1 here gives you the number of radial rings. But if I don't get the sort of alignment quite right in the experiment, so here I added a small Gaussian, these dark rings break apart, and I just get a forest of vortex lines. And one of the reasons why these are very easily controlled by holograms, and they're useful both because the phase, the direction of the gradient of the phase gives you the direction of the Poynting vector, the energy flow in the wave, and so the vortex means there's energy circulating around that's useful in optical tweezers. Also, because it's a minimum of intensity, that gives us very localized sort of null surrounded by a large intensity if you're putting it into a liquid crystal that causes alignment. Having a dark blob in the middle is useful. And one of the main relations, the people in optics find these things very interesting, liquid crystals interesting, is because holograms, as in spatial light modulators, are what is used to create these vortex beams. The hologram has a phase going around the axis of 2 pi. And once you've got a vortex on the axis, that carries helicoidal wavefronts, as you can see just by taking, say, the real part of this function. And so you often see, and it was even in the news at the weekend, people have managed to embed these things propagating into optical fibers, and it means that using the topological number on the axis, some integer, you can actually increase the information content that you can transfer down optical fibers. So it's seen as a hot topic, topological optical communication. This was New Scientist's take on it a few years ago. Twisted light, you can't read it, it says, it's fast, it's furious, and perfect for talking to aliens. The question was, if this light can be detected with this helical nature coming from the cosmos, then that's probably because ET is trying to tell us something. And just a couple of years ago, there was an experiment of using radio communication with this helicoidal radio, our microwave antenna, to across the Grand Canal. So there's quite a lot of interest in this stuff in optics, and it has quite a lot of relationships at different levels with liquid crystal physics. One of my interests, which will relate to something that Professor Zhumer will talk about tomorrow morning, is how one can use the superposition principle. So you can take these Laguerre-Gauss modes with these different weightings of L and P and add them together in order to get a vortex that's tied into a knot, using some mathematics that I will not talk about. So these vortex lines can be controlled by interference, just as you might control defects in liquid crystals by other means. And if you just let light go, randomize it by propagating through a ground glass screen, getting a speckle pattern, you get these bright blobs, and amongst them there's a forest of these dark lines. And so there is this topology in random light all around us, and looking more, this is from an experiment, but looking more systematically in simulations, one can get linked vortex loops, and even if you look at it closely, that's actually a trefoil knotted vortex. So that's an idea of some of the things that people are interested in scalar defects of light, that is to say, optical vortices. So now I want to talk just a bit about spatial order from optical polarization. So if I'm not just now talking about a scalar component, I should be talking about a complex vector, not just Ex, but Ey. And I can separate that into real and imaginary parts, my complex vector. And again, just as before, the real electrical field is this complex field times e to the minus I omega t. But you can now do a little bit of that trick that I was trying to avoid by expanding this out. So what the real electric field does is it's some time-dependent superposition of P and Q, which are just a couple of vectors. And as time varies, it turns out that the E field sweeps out a polarization ellipse. This is where elliptic polarization comes from. When the polarization ellipse has got, well, the ellipse has a major axis, which gives us a director, an axis angle theta, and we also have a shape parameter, the eccentricity or the ellipticity of the ellipse. And typically when thinking about polarization, we ignore the size of the ellipse, the overall intensity, and the vibration phase, which picks out where the real part was. Of course, it's changing very, very rapidly. And in fact, the description of polarized light in optics, we tend to use Stokes parameters, is very similar mathematically to the Q tensor that's used in describing crystals. So effectively, the Q tensor for light is the average over time of E star tensored with E, but this is a complex vector rather than a real vector like if you were looking at, say, an ematic. And this average is what we would do when we talk about partially polarized light. So I have a little 2 by 2 matrix like a Q tensor, and because it's complex, I have a complex part in the off-diagonal elements here. And the components S0, S1, S2, and S3 are the so-called Stokes parameters that are easily measured in a polarization experiment by S0 is the overall intensity. S3 one gets by taking the projecting with a right-hand polarizer and subtracting off what you get if you have a left-hand polarizer. And S1 and S2, what I get if I have a vertical polarizer minus what I get with a horizontal polarizer. S2 is a polarizer at 45 degrees minus what I get with a polarizer at 135 degrees. Now, if I make the complex combination of S1 plus IS2, I get something which can be thought of as a sort of nematic complex scalar order parameter. So this is this sigma plane. So if sigma is just in S1, S2 is 0 and S1 is positive, that means the polarization is horizontal. If S1 is negative and S2 is 0, the polarization is vertical. And in fact, as I go around the origin, you can see that the major axis of the ellipse, it rotates by 180 degrees. And you could ask, well, what would happen if I filled in all of the lines around that pattern? And what I get is that plus half disclination pattern. The plus half disclination pattern comes very naturally simply from looking at, from saying that you've got a pattern where the rate of rotation is simply half that of the azimuth around the defect. And in this case, the distance from the origin is the degree of polarization, the ellipticity of polarization. And if you look at, again now, a random pattern, but this random pattern now has got spatially varying polarization, you see rather complicated patterns where the directions of the ellipses vary. The dark is supposed to be right-handed ellipses rotating around, the white is left-handed ellipses rotating around. And this was first considered as a problem by my colleague in Bristol, John Nye in the 1980s, and in the coffee break I actually found a picture of him when he was a graduate student here in Cambridge in the 1940s, and there he is. He doesn't look like that now, he was 90 earlier this year. So there are different sorts of defects in this pattern. There are so-called L lines, lines which separate the region of right-handed and the region of left-handed polarization, which is a bit like phase separation. And there are isolated points in this pattern where the polarization is purely circular. So-called C points, points of circular polarization. And they can be detected looking for zeros and Stokes parameters. And effectively, when the polarization is circular, this complex nematic order parameter is 0. And so looking at two of those patterns, one can see they have index half with either plus half that looks like a regular plus half defect and minus half with this threefold symmetry. And these are the sorts of quantities one uses to define them. And in fact, this idea of director singularities that one sees in liquid crystals and non-optics are also very generic. We see them in displanations, we see them in the patterns of Skylight, those are the things I showed you at the beginning. They appear in the curvature on surfaces. There's defects of the most directions where the curvature is the strongest and the weakest, the so-called principal curvature axes, and they occur in growth patterns. I don't know if you've seen these patterns, which are the orientational sensitivity in the visual cortex. This is an experimental measurement of a cat's brain, and in your brain, in the visual center, when you see something that looks a little bit vertical, the vertical nerves fire in that little patch of the brain. If you see something at 35 degrees, whatever's at 35 degrees fires. But of course, this is a spatial pattern in your brain. And of course, if you want every part of your visual field to be maximally sensitive to all of the directions, you need to have a lot of defects there to be able to pick up as many directions as you can around every point. And so these pinwheel patterns, so-called, are a known interesting phenomenon certainly in mammalian brains. And finally, one sees a plus half defect and minus half defect typically on fingerprint patterns. The sort of thing that is used in optics where these polarization singularities are useful is often related to looking at optical vortices. So, for example, taking one of these Laguerre-Gaussian beams with a vortex and propagating it through a homogeneous crystal, birefringence causes this pattern to separate into two, and so this is a typical intensity pattern out on the other side. But in fact, the two copies of this have different polarizations, are spatially separated, and acquire relative phase shift. And so, in fact, the polarization can be quite complicated, and these polarization defects are a very useful way of tracking what happens to the polarization. For example, as the relative phase shift increases, one gets complicated geometries of three-dimensional defects. So in the final few minutes, I'll come to this topic, light propagating in crystals, and how all of the stuff I've been talking about is related to uniaxiality and biaxiality in homogeneous crystals. So, when we're talking about crystal optics, I'm just talking about what you find in the textbooks. So I've got linear dielectric anisotropic material which is homogeneous. It's the same at every point in space, it's not different. I'm not worrying about absorption, I'm not worrying about chirality or anything, it's just the textbook case as on this front of this old textbook. And when I'm in a crystal, the most important thing is to realise that the electric field is not the same as the displacement field D. And we have to use the fact, when we're thinking about Maxwell's equations, that it's the divergence of D that's 0 and I don't have any charge. It's not the divergence of E. And of course, D and E are not necessarily the same. They're related by the dielectric tensor, relative linear electron response, which is different in different directions. No, not very complicated, no position dependence here. And that means that this relative dielectric tensor is a real invertible symmetric matrix. So this is how to understand birefringence. So when I've got a crystal like this, it's calcite, you can see there are two images of the word calcite behind this crystal. If it's biaxial between cross polarizers, I see these complicated patterns like here. And of course, these things, in a more complicated way when this stuff is all position dependent, is what gives rise to the Schlieren textures of liquid crystals. So, I'm running out of time, so I'm not going to go through the manipulation of Maxwell's equations, but by manipulating Maxwell's equations and choosing to work with D, because it's D that's divergence free, so it's going to be D that's perpendicular to the k vector of a propagating light beam, Maxwell's equations say that the polarization D has to satisfy this equation, where this P perpendicular to S is the projection in the plane perpendicular to the direction S that the light beam is propagating. So this is an equation that says if I've got light propagating in a direction S, the polarization has to satisfy this equation. And what is this equation? Well, what I have is I've got this epsilon r, which is like a tensor. I could use it represented by an ellipsoid in space. And I'm projecting into the direction perpendicular to the one I'm looking in. So if this was my ellipsoid, I'm projecting the ellipsoid into the plane perpendicular to the one that you're looking at. Of course, when you look at something, that's always what you do. I've got what looks like a three-dimensional ellipsoid, but actually all you really see is the outline of the ellipsoid in that direction, which is an ellipse. And effectively, when you look through a crystal, that's what you're seeing. You're seeing the ellipse that's perpendicular to the direction that the light is propagating. And that ellipse has two axes, a large one and a small one, and those are the related to the refractive index, the speed of the light propagating through, and the directions of these axes are the directions of the polarization. So the eigenvectors and eigenvalues of effectively this linear matrix equation can be thought of geometrically as the axes of the projected index ellipse. And if you want to see more details, this is what is often called the Fresnel ellipsoid in textbooks. So what I've got is I've got this equation. It's a matrix equation. Effectively, this is a matrix acting on D, and here's an eigenvalue because it's times by D. So I've got two eigenpolarizations, two solutions of this equation. Of course, there's a third one, which is the direction S itself. If I project S into the plane perpendicular to S, I get 0. So I'm interested in the other two solutions that are perpendicular to it. And it depends on this epsilon here. And optic axes, so-called, are the directions where I play this game where this looks degenerate. That is to say, when the projection of the ellipsoid looks circular. Because when I have something that's projected to a circle, I can't see what the long axis and the short axis is. So, for a uniaxial crystal, it's represented by an ellipsoid of revolution. And of course, if I look down the axis of the ellipsoid of revolution, it looks circular. And from this geometry, the eigenpolarizations are also always perpendicular and parallel to the optic axis. It's like, I'm just going to want to spill water everywhere. But if I take this, here's looking straight down it, if I perturb it a little bit, these are the two directions of the polarization in a uniaxial crystal. Whereas if I have a biaxial crystal, the ellipsoid axes are different. Although all three of them are different. In that case, I have two optic axes. When we call it biaxial, it's these optic axes we're talking about, the directions where the ellipsoid looks circular. And if you want to see how that works mathematically, the ellipsoid matrix in IJ form is, for the optic axis UV, it's UIVJ plus VIUJ times something plus some diagonal stuff. And you can always put a real symmetric matrix into this form, and it's the U and the V that, when you project perpendicular, it looks circular, and those are the things that we're referring to when we're calling something biaxial. Because optically, those are the most interesting directions. The eigenaxes of the ellipsoid, are less interesting from an optical viewpoint. Because if we look close to a uniaxial, we see this pattern of the polarizations around. The ordinary polarization is concentric circles, extraordinary is radial. And looking through cross polarizers, one sees this usual 4 brushes. And that's because when we've got this polarization pattern, but if one's looking through cross polarizers, say horizontal and vertical, the polarizer, say it's horizontal, cuts out there and there, and the analyzer, which is vertical, cuts out there and there. And so no light gets through on those axes. Whereas if it's biaxial, you actually see the 2 extraordinary polarization patterns both look like one of these +half disclination patterns. And now, if I have horizontal and vertical polarizer and analyzer, it only cuts out the up-down. And I've got a demonstration I can show you afterwards if you're interested to actually see these optic axes quite simply, and you get only 2 brushes now rather than 4. And the radial, these concentric circles come about because the phase shift increases as one moves away from that degeneracy. And finally, I go back to what I started with at the beginning and talking about the pattern of polarization in the sky, which turns out to have a very similar geometry. Because if I'm thinking about light in the sky, what's happening is the polarization is multiply scattered around. So I'm looking at a direction in the sky, I'm seeing a mixture, just like when one's looking at the at pneumatics and one's taking the average of all of the molecules. Here we're taking the average of the direction in the sky of all of the different polarization vectors. And one gets some sort of biaxial ellipsoid object, some sort of Q-tensor. But the geometry of Rayleigh scattering means that if I'm looking at that direction, I don't see any of the polarization that's in the direction that I'm looking. I only see the polarization perpendicular to the direction I'm looking. So the complicated integral differential equations of multiple scattering, it turns out you can write them as a series like this, where I've got the direction, the projection perpendicular to my looking direction, and then treating the thickness of the atmosphere as a small parameter, I develop a perturbation series. And this was actually done by my colleague in Bristol, John Hannay, and this is the picture of him from out the front. So these are complicated functions of the thickness of the atmosphere, the height of the sun, and also observation direction. But significantly, if the sun is significantly far above the horizon, and I'm looking above the horizon, the leading order here becomes independent of S. If it's independent of S, I just have a fixed Q-tensor for all directions. So I'm taking that same Q-tensor, but I'm looking at that Q-tensor in different directions. When I'm looking at it in different directions, I'm effectively sampling this ellipsoid from all of the different directions of looking, and I get here those defects, those +half defects in the sky, are the directions where that Q-tensor of polarizations looks circular. So the pattern is exactly the same sort of pattern as one sees in a biaxial crystal, and here's the result. I'll talk about that in detail. I'll leave you instead with a quotation of David Brewster, well known for his research in polarization. It is not one of the least wonders of terrestrial physics that the blue atmosphere which overhangs us exhibits in the light which it polarizes phenomena somewhat analogous to those of crystals with two axes of double refraction. So you can see the connection between crystals and light, blue sky research can lead us to new insights. So to finish with, I've shown you how scalar light has defects, which are optical vortices. They organise the optical topology and can be manipulated holographically. Optical fields have half-integer defects coming from polarization and occur typically in scattered light. The term biaxiality comes from thinking about optic axes of crystals, and there are two disclination-like polarization defects in direction space, and crystal-like geometry, including the axes and the defects, describes the skylight polarization pattern. And the thing that I didn't have time to tell you about is how the shape of optical disclinations is different from liquid crystals because there aren't any energetic considerations. And I can go into that in more detail if you come up and speak to me later. But for now, that's it.
Questions, please?
So I find this absolutely fascinating. Just a question of clarification. Towards the end, when you talked about polarization of skylight, you seem to imply it's multiply scattered. Am I to think each photon is then scattered at several scattering centers, and then you're looking at the overall polarization, or it is from a single scattering event that you would look at the polarization in different directions?
Okay, good. So I sort of rushed it a little bit at the end. So there are different ways of thinking about it. The first is to say we're certainly not talking about single photons here. For example, we're talking about white light. So of course we're talking about all different frequencies. But this sort of, the geometry of what's going on is sufficiently generic across different frequencies that one can treat it in this way. So what we're thinking about is, the fundamental thing is, with this approximation, effectively, what we're treating is that the entire layer of atmosphere above us is approximately a uniform layer. It's like a stratified medium. And so horizontal light comes in from the sun and is multiply reflected, but because everything is translation invariant in that plane, every point effectively in that layer has the same Q tensor. And so the only thing that varies when we're looking in is actually the different directions that we're sampling the Q tensor from our observation point. Okay.
More questions? I think we can get a very important lesson from this talk, from the connections which are in mathematical physics between completely different, on the first sight, physical phenomena. And that's why physicists, well-educated physicists, can work in any field.